VDS, and this is the ID. Characteristic and the plane is divided into two parts. One part, which is along a parabola, which is a locus that divides saturation region. This is called saturation region. In other words, active for analog application. Analog application, we use the saturation region. For switching application, we use to the left of that parabola, which is called the ohmic region. Here, to the left of the parabola. This is called as triode or ohmic region. Used for switching. Used for switching apps. Used for switching applications. So the characteristic of the VGS versus the VDS follow a particular pattern. First, ID will be 0 for VGS less than VT, which is known as the threshold voltage. Threshold voltage is usually a voltage which is necessary for inversion in order to create mobile charge between the drain and the source channel. So once the gate voltage exceeds, there is enough electric field between the insulated gate and the substrate that it motivates and electrons come underneath the plate. And then there is an N region, two N regions. One is for the drain, one is for the source. And once we have mobile electron in all three regions, in the channel, which is inverted into an N-type, and the source, ditch, basically, where the source ditch is, and then the drain is, these are all N-types. When there is enough voltage at the gate, electrons come to the surface and current generally picks up. Current can travel by mobile electrons between drain and the source. Otherwise, between drain and the source, we have exactly the same situation. We have two diodes back to each other, which are unable to conduct anything. But there, you can do it if there is enough voltage. But the gate to source voltage equal or less than VTH, there will be no current. You may have a voltage there, but if it is 0.1 of a volt, the transistor will not invert, enhance the electrons. Enhancement comes in when it exceeds a set threshold value. Now, after we change the VGS to a higher level, the mode of the current transfer through the drain to source changes between two. Number one, initially it will be proportional. So just like a conductor, just like a resistor, for VGS slightly greater than the threshold voltage. Initially, it will be a complete linear relationship between ID and the VDS. That is why, starting from origin, that is why this region picks up like the characteristic of a resistor. If between drain and the source we had a pure resistance, current, drain to source voltage would be proportional forever. It would go up forever. But it doesn't happen because this is a semiconductor. In the semiconductor, when we exceed a certain level, the amount of the electron available in the channel will reach a saturation stage. In other words, the current will start flattening. So after this picks up from there, for a while it is linear, but slowly it will bend, and eventually it will become a constant. For VGS, let's say equal to 1.1 times the VT, some 10% greater than VT, threshold voltage, we will get a constant current in the transistor. So initially it will be linear, and then it will become a constant current, like the transistors. IC is a constant, independent of the VDS, theoretically, independent of the VDS. If you increase VGS to multiple times of the VT, for example, if you increase VGS to here, VGS to 1.5 times of VT, say 50% more than VT, this is 10% more than VT, same thing will happen. But the law between ID and the VDS, this law will be linear, just like a resistor, but it will be steeper. Steeper means this will be a smaller resistance because there is more conductivity for the same voltage. See, if you take a voltage here, lower curve conducts less, upper curve conducts more current. It's like a resistance being smaller. Because what is resistance? Resistance is 1 over slope of the IB, right? So slope in here is less than the slope over there. Therefore, 1 over the one that is less is greater than 1 over the one that is steeper. So it becomes a smaller and smaller and smaller resistance. Indeed, there is a VGS value called VGS on, which the resistance in the origin will become so small in the order of 20 to 30 milliohm. 20, 30 milliohm is like a short circuit, almost like a switch being closed. There is no resistance across, therefore there will be no voltage drop in it for appreciable amount of current. And so on. So the set will continue. That region is called the triode or ohmic region, will be named that. There are a set of equations pertaining to this characteristic for analytical purposes. I will state them, condition them, and then we will develop the small signal equivalent circuit based on those equations, okay? So that's the major characteristic, ID against the VDS. However, if you ensure that you're operating in the saturation region where the lines are horizontal, there is another more popular characteristic. Here, when something becomes horizontal in the VDS plane, that means delta of ID, change of ID with respect to delta VDS is 0. That means ID is independent of the drain to source voltage in here. Obviously, see? It's determined solely by VGS, not by the VDS. You can be here, you can be there, as long as you are at 50% more than VT. Doesn't matter what is VDS, your ID will be fixed, a fixed quantity. So when that happens, then your ID becomes dependent on the VGS very strongly. So we can create another curve, very practical. This is called the transconductance curve in saturation region only. It's only valid there. This transconductance curve looks like ID as a function of the VGS. VGS plays no role in this function. The curve resembles to a parabola that starts from a point called V of the T, threshold voltage. So from 0 to the threshold voltage, there is no current. Here it is, that curve, lying on this axis. For VGS less than VT, there is no current. And then after you apply a VT, some percentage of VT, the current will pick up. The curve will be essentially a parabola to the nearest approximation. We are going to model them with equations in a minute. So this is called the transconductance curve. ID against the VGS, meaning ID is controlled by the VGS only, not with the VDS. So if you have a bias point here as ID quiescent, a VGS quiescent, if you have a bias point, just like the IB and the VB of a transistor, then at that point there will be a dependency between a small change in the VGS and a small change in the ID. Again, same story. If you look at the small changes, quite limited in this range, here, this chord from the curve could be almost considered like a line. Therefore, for small changes of the VGS, the small change in the ID will be proportional and linear. We can apply that concept to every nonlinearity. Every nonlinearity in a small range is linear. Let's put it this way. Okay? So the tangent here, tangent to curve, which is delta ID to delta VGS, is called GM, transconductance. Actually, we should say small signal transconductance. The unit is the same old one, S, Siemens. So the delta ID will be substituted by a small ID, delta VGS by a small VGS in the model that we're going to derive. So this is the story. If you're operating here in the saturation region, this is your model. We can linearize it, linearize with a constant value. In other words, then if you substitute delta ID with little ID and delta VGS with little VGS, lowercase VGS, then ID will be equal to GM multiplied by the VGS. Okay. multiplied by VGS, gate to source voltage. Just the same way that IC was GM times VBE, here it will be ID equal to GM times VGS. Either you can obtain GM mathematically, like the transistors, IC over VT, that was called GM, or you can do it here, calculate GM through the equations that I'm going to put it on the board in a minute. That is like from the mathematical models. Customary is, analytical is mathematical models. You know, we derive from them. Okay, so this is the characteristic. You have seen, you have already been introduced to the FET structure. It has a P-type. See, this is a P-type substrate. Then it has two regions, N and N region. One is named source. The other one is named, with the contact is brought out as drain. This bottom one is a plate which is also brought out. It's called B, body. Always BS must be less than or equal to 0 in order for the transistor to function. In other words, your B has to have a potential lower than the source. So if the source is 0, guess what? This can go negative to -1, -2, -5 volt, arbitrarily. You can take it wherever you like. But up to B equal to source, VBS being equal to 0, it functions. It functions. When B is connected to the S, that model will apply, because that is the S, but this part is the B of it, this contact. So that is the S, that is the B, and this is a P-type substrate, and the B is the open terminal. We can usually connect them to the S, and therefore we can make a 3-terminal device. If you're getting a MOSFET that shows 3 pins, the manufacturer internally has connected the body into the source, and you cannot separate. It's inside the chip. But if you buy a MOSFET with 4 wires coming out of it, then manufacturer hasn't done that. SD1 will be the gate. In a minute I'll put it up there, and the B will be a separate terminal coming. It is up to you if you want to connect the B to S, depending on your application. If you're doing amplifiers, just do that, connect the B to S. So you will buy 3-terminal FET. But if you're going to work it as a analog switches or gates or anything else, multiplexers and so on, then B has to be connected to a lowest potential in the circuit. And guess what? Look at this symmetry. The transistor can switch duties. That terminal can work as S, this can work as drain, and vice versa. This can work source and drain. So the current can come in, get out of there, depending on the potential you're putting on the drain to source, or current can come in this way, get out of there. This way or that way. If this is positive to that, current will come through here. If it is negative with respect to that, this is positive to that, the current will come in through that terminal, exiting there. Provided all the time this condition applies. So this will change its name into S. Your VBS must be negative. In other words, this has to be sufficiently negative with respect to either one of these electrodes all the time in that application. For example, as a multiplexer, if this is ranging between -2 and +2, this is ranging between -2 and +2, then body voltage has to be less than -2. If it is less than -2, it doesn't matter which one is which, still it will work successfully. The current can come in either way. Now, the next thing on that is the gate. Gate is at the top here. This is the gate. By putting a positive voltage on the gate, here, positive VGS, you create an electric field here, which will bring up electrons from the p-type material. First, it will create an inversion layer in here, and then it will enhance the number of the electrons just underneath the surface. So we can capture electron, electron, electron here. And because N-type already has its natural electrons, it's a donor, it has the electrons. If you put a positive voltage in here, negative voltage in here, electrons will move that way, meaning current will go opposite way. If you make this one positive with respect to that, again, electrons will move towards the positive pole of the battery. Current will come in the opposite direction. But without the electric field or insufficient electric field, that means insufficient gate to source voltage, this phenomenon will not happen. Electrons will not be enhanced. It will be blank. If it happens to be blank, you have N, P, and an N. These two look like reverse diode. Look, it looks like this. Two back-to-back diodes. So if you put positive voltage with respect to that one, this diode will not let the current to flow. If you make this one positive with respect to that one, this diode will not let the current flow. Just because the region is void of charge carriers. You must have homogeneous charge carriers from end to end. Either all holes, which would be the p-channel MOSFET, then p-channel MOSFETs have N-type substrate. N-type substrate and p-type drains and source. That's the p-channel MOSFET. The N-channel is opposite, has N-channel, N-type drain and the source material, but the body is going to be a p-type. So the force, electric force in the gate to the body will encourage the electrons to come to the front and align themselves homogeneously in that region. And the more gate voltage you put in there, the thicker and thicker this layer gets. Thicker and thicker, more electrons are building. That's why the more gate to source voltage you put, this resistance gets smaller and smaller. Conductivity gets better and better. So when you put a gate voltage to that, up to a certain range for small drain to source values, it will be a linear one. But as you increase drain to source voltage, given the VGS value, there is only a limited number of electrons that can exist underneath that. So the channel shape doesn't go linear, but it tapers like this. Tapers, and as a result, we will get less conductivity, less mobile electron available there. Therefore, the current will reach to its saturation, leveling over there. That's the nature of semiconductors. Semiconductors, when you pass a current, like one bar, you pass a current, they look like resistor here initially. You put more voltage on it, their current will increase, but eventually will flatten at some point. There will be no more extra current. Okay, so this is the structure of it, just to remind you. And naturally, because it's a gate insulation, there's no contact between here and here. At high frequency, it is capacitive, because this is a capacitor. DC wise, there will be no current flow through this capacitor. So IGs are condemned to be 0. No current there. Equations. So I'm going to list the equations for you. FET equations. So number 1, ohmic region. Ohmic region. ID is going to be equal to Kn times VGS minus VT minus 1/2 of VDS times the VDS. Only for the condition if VDS happens to be less than or equal to VGS minus VT. So if your drain source voltage is small compared to the difference of the gate to the VT, the transistor will obey a parabola. This is a parabola, ID against the VDS. It's this parabola. Near origin, it's almost linear, but then it starts bending. Okay? In that range. For very small drain to source voltages, so we are talking about very small drain to source, near origin. Near origin, when VDS is much smaller than VGS minus VT, when that is the case, then this term can be deleted, comparison to that. ID will be equal to Kn times VGS minus VT, empty in here because that's small compared to that term, multiplied by VDS. Now this is equation of a line. Y, M, X. This is equation of the line. Which line is that? It's this lines that animate from the origin. They extend out from the origin. They initially start linearly. And this is the relationship, line passing through the origin. So VDS over ID, voltage divided by current, by definition, is a resistance. So this is called RDS, is equal to 1 over Kn times VGS minus VT. This is known as drain to source resistance. Drain to source resistance. When VGS acquires its maximum value, there's a limit to the VGS because more voltage you put on the gate with respect to the substrate, you build a stronger electric field underneath the plate. Remember, plate separates from the body by only a few micrometers, like 2-3 micrometers, maybe 5 micrometers, nothing more than that. So if you are putting 5 volt on 5 micrometer distance, your electric field is 1 megavolt per meter. 1 megavolt per meter is seriously very high electric field. So high that it might even break down the insulation. There is an insulation which can resist only so much electric field. So there is a limit on the gate to source voltages as a result of that. You can put arbitrarily whatever you like. But there is a maximum you can put. VGS maximum. Yes?
For the second ID, is that if only happen if VDS is above VGS minus VT? That
This is VDS over ID ratio. This line is expressed as that. Any problem there?
I'm just wondering, so that only happens if VDS is larger than the
No,
VGS?
this happens if VDS is much, much smaller than VGS minus VT. For example, if VT is 1 volt, VGS is 3 volt, and your drain to source voltage is 0.1 of a volt, 0.1 is much, much less than 3 minus 1. Then automatically the link between ID and the VDS will be line, like this, like a resistor. So you can model your transistor subject to that condition, this condition. You can model them simply, guess with what? With G, a resistor, RDS, drain, source, VGS. And this is the VDS. And this is the ID. IS equal to ID. So we don't have that current source business. You remember, IB against the IC was a beta times. You don't have beta in here. It's just that. 3 terminals, one is gate, one is drain, one is source, and a resistance is posted over there. This happens when VDS is much, much smaller than VGS minus VT. That means near origin. Near origin. Okay? So, what is then RDS on? RDS on, known as on resistance, on resistance is equal to 1 over Kn VGS max minus VT. The VGS max is often referred to as VGS on. This VGS max, because it's a maximum, is VGS on, recommended on voltage. So go by that, recommended on voltage. Maybe they can take 16 volt for the maximum before they are busted, the breakdown. If manufacturer says 16 volt is breakdown, but VGS on is 12 volt, go 12 volt, no more than 12, because it will break down the transistor. There are chances of it. You will get smaller resistance, definitely, if you go higher than VGS on, but it's risky. Okay, so VGS on when it is used as a switch. As a switch. Automatically, this resistance will become infinity. RDS on, RDS becomes infinity if VGS is less than or equal to VT. That's promised it will happen. So if it becomes infinity, guess what will be this model? Look at these 3 points, drain, source, gate, like 3 nodes. If this is infinity, it's a 3-way open circuit. You see that? 3-way open circuit. Because RDS is infinity under those conditions. Then your switch will be open, voltage can be anything, it's drain to source voltage can be anything, it's open. Or if you apply VGS on, the RDS will go low, awfully low, but to a limit. I mean, it can't be short circuit, that 0. The lowest in switches will be in the order of milliohms, like 10 million, 0.01 of an ohm. Now, 0.01 of an ohm, it can pass 20 ampere, leaving only 0.2 volt on it. 20 ampere is quite a current, you know, it can run a motor, electric motor. So it is not that it's not going to get hot. It will, because when the current gets real high, eventually you have a small resistance there, therefore a voltage drop, therefore you have I times V product, and there will be some kind of a power dissipation in the transistor. Though small, but it will be. So next one, this was the exact equation which explains all over the ohmic region, all the way to here. And this one specifically only for the origin. Here I wrote there, drain to source resistance is equal to that small signal here, near the origin, near origin. That condition applies to the near origin as a on and off switch. Now the next one is the saturation region. So once we get to the saturation region, there VDS, drain to source, becomes greater or equal to VGS minus VT. So that was less. This one is more, equal or more. What happens when they are equal? I will show you what happens then. So when it is greater or equal, we will get ID equal to Kn, which is a conductivity constant, over 2 times VGS minus VT to the power 2. Often it is modified with a coefficient lambda times VDS, which makes the drain somewhat dependent, drain current somewhat dependent on the drain to source voltage. Now, that arises here, allowing for the fact that the lines are slightly slant, and this is when lambda is greater than 0. Lambda is called channel length modulation index. The unit of that is volt to the minus 1. It's the reciprocal of volt. It has to be reciprocal of volt, because look at that. This whole parenthesis is unitless. Because Kn is amperes per volt squared. This is the unit of Kn. This is volt minus volt is a volt. This is a volt squared. When the two multiply, it becomes amperes. ID is in amperes, or milliamp, we will use it later. So this parenthesis has to be unitless, like number. In order to make it unitless, because VDS has a unit of volt, lambda has got to be volt to the minus 1. Got it? Lambda has to be inverse of the volt. But how do you calculate the lambda? How do we figure out the lambda? It's from the characteristics. If you experiment with VDS ID and you see a line like that in SAT region, this line will intercept that axis at a position called minus 1 upon lambda. It is analogous to VA, early voltage in the transistors. So experimentation is easy. Go get the characteristic ID here. This is ID against the VDS. Get 2 points on the line in the saturation region, extrapolate that line. Wherever it cuts it, figure the voltage, flip that voltage, and that is your lambda. Okay? In an ideal case, here, in ideal, lambda will be equal to 0. That makes the lines horizontal. So it is a equation adjusted, basically. It's a mathematical model. This is a mathematical model. So if we want to use the transistor really analyzed based on the data available, we should know what the lambda is. But mostly, people disregard lambda. Lambda is equal to 0. So here, I will write the ideal. Ideal FET. Lambda is 0. Equation is ID equal to Kn over 2 VGS minus VT squared. This equation, gentlemen, is exactly the curve that I drew earlier. VGS, ID, and the curve. B of the T. In this equation, VT, ID is 0. ID will be equal to 0 if VGS happens to be less than or equal to VT. ID will be 0 if that condition applies. In order to allow for this fact that gate to source voltage has to exceed a threshold for the parabola, this parabola to follow. So you have no parabola here if VGS is less than VT. You have to be careful about it. Now, about that slope we were talking. Here. Slope at Q point. How do we determine that slope at that Q point? You'll differentiate this equation here, delta ID over delta VGS with respect to the gate. It's just a simple parabola. You get Kn times VGS minus VT. This quantity, small change in the ID due to a small change in the gate to source voltage, is called GM. GM of the transistor. So this is one formula that allows you to calculate GM. From the knowledge of the VGS, you can determine GM. Or an alternative one. Alternative one would be if you eliminate VGS between this line and that line, you will get GM equal to radical 2 Kn ID, quiescent. ID quiescent is the current ID Q. So this is VGSQ, this is VGS quiescent, and that is the slope, operating point, the Q point. So that is another formula which calculates. It's the same thing, basically. All we have done is to eliminate VGS between here and here to to change the GM as a function of the ID. Okay, so we will be frequently using that for our GM when we're doing calculations. So what is the small signal model? Can't be even easier than this. Simply, small signal model would be a current source even better than the BJT. So this will be little s. This will be lowercase g. If you recall, we used to put lowercase b for the base of the transistor. We kept the uppercase B for the biases. An opening here, just dead open. This voltage will be marked lowercase VGS. That's the tiny increment from that point to the left, to the right. It's this VGS operating to the left and right of the nominal VGS, which is the Q. And then here you would have a drain D, and this current would be ID equal to GM multiplied by VGS. Small change in the VGS. That's it. It can't be any simpler than that. However, if in case you happen to have lambda here, it is possible to show that you can add a resistance between these 2 points known as RDS. This is the drain to source, drain to source dynamic resistance. It is like RO of the transistor, which used to be in the transistors. We used to have here. In BJTs, between collector to emitter, C to E resistance was equal to RO equal to it was VCE quiescent plus VA early voltage divided by IC. In the case of FETs, however, there's a smart way to apply it. This is how you do it. Do you remember what I wrote in here? 1 upon lambda is analogous to VA. So simply substitute for VA 1 over lambda. And you will get this one. Here. RO, RDS, let's call it RDS, is equal to VDS quiescent plus 1 over lambda divided by ID. Which translates into RDS equal to lambda ID. You know, these are what textbooks are using. Lambda ID, and also 1 plus lambda VDS. There we are. That's what it is. So here is the situation. If you know the lambda for a transistor, yes, you can determine the dynamic resistance. No problem there. How do you do that? If you know the Q point where you're operating in the plane, ID, VDS, and you know the lambda, stick it here, incorporate here in your small signal model between drain and the source. That's it. And your GM is, this current source is ID equal to GM times VGS. Actually, this is the GM VGS. That's the current source. So if there are drain, other resistances from here to the ground, etc., we will just show it in the model. Here is the summary of the FET. Okay, so let's see what I did. Very briefly, I just jot that down. Structure. It looks like a symbol like that, but generally the natural FET doesn't have this link. It's actually 4 wires. Natural FET is 4 wires. But when it comes to analog operation, if we want to keep this as a drain all the time, in other words, if you want to make sure that this is not going to become negative with respect to the source, then you can join B into the S, and therefore people put a short right there. This is the model that I like it. Alternative. There are many symbols. Unfortunately, it's not like BJT. There are alternative symbols for this one. Look, here is how it is. First of all, the idea of this broken line. What does the broken line mean? It means that there is no homogeneous media or semiconductor between drain and the source. There's a break. You have N, you have P, then you have N. Break, okay? If it was a different type of a MOSFET, known as depletion mode MOSFET, there would be a layer of N between drain and the source deposited there. So we would have an N type already built. Therefore, when gate to source voltage was 0, in that case, if you had this layer built into the MOSFET, in here, pre-built layer, thin N layer, no problem for the conductivity. Because even if you put gate to the 0, to the ground, S to the ground, if you apply positive voltage to the D with respect to the S, easily electrons will be attracted towards the positive pole of the battery, because this will donate. Electrons are mobile here, electrons are mobile here, homogeneous N type, the current will flow. That kind of a transistors, the curve is not starting from the VTH. They don't have VT in this region, but rather the curve starts from here. So when VGS is equal to 0, you will have a current flowing through the transistor. This is called the depletion mode MOSFET. Extensively used in analog devices, in communication devices. Actually, it is the most favorite in the communication device. You know why? Because you don't need to bias gate with respect to source with a voltage divider. All you have to do, just put the source, AC source from here to here, straight. No biasing necessary. If you put AC source from here to here, your VGS DC will be 0. That means you will be operating in here, up, down. That will give you actually a maximum GN in here. Quite a maximum slope, which means gain. The higher GN, the more is the gain. So those are perfect for analog communication devices. For digital devices, this one is perfect. So that below a threshold level, there will be no conduction. And it is logic compatible because all voltages are 0 to positive. This one is not logic compatible because voltages are negative going to the positive. So this is the structure, and I talked about the buildup of electrons underneath the layer from the p-type by influence of electric field coming from the gate, which is due to the gate to source voltage. So once the field exceeds, it will attract electron from the bulk, lay it underneath. Electrons can conduct then. Initially, that layer gets thicker and thicker for small drain to source voltage. So layer gets thicker, it means resistance will be proportional to the VGS. That will be the linear region, just like a O. But once the drain gets higher voltage, it will influence distribution of electric field. It won't be uniform anymore, it will be inclined, 0 will be there will be a positive there, and the region will shape into a triangle. That means it will reach a limit. Channel will not thicken any further. It will reach a limit, therefore the current will reach a limiting point, saturation point. That region might slightly retreat like that, aparting from there, leaving a gap in here. And when it leaves a gap over here, we lose homogeneous movement of electrons. But electron between here and here can diffuse actually through the p-type material. Although p is not the same as n, but it can diffuse. That's what happens in BJTs. You will say, how come electrons are moving from emitter getting to the collector? Well, they diffuse through the base. It's a different type of a material, but they can go through because of their energy. So it's pretty complex, let me tell you, about the operation here when we get into those regions. Electron flow is by diffusion. I'm not going to spend time on that. And as a result, the drain to source voltage affects the actual value of that, the modulation of that channel, because channel gets shorter or a little longer with the drain to source voltage. That's why we get this slope. So I gave you the characteristic ID against the VDS, and I said drain is controlled by the gate to source voltage. If you're operating in the saturation region here, then this is your another equation, very convenient. It's called the transconductance equation. It's an ID as a function of gate to source, perfect for analysis. You can use load line, everything to get the solutions. Equation-wise, the ohmic region follows those lines. In the origin, which is like deep into the triode region, right there, here, for switching purposes, then literally MOSFET becomes a resistance between drain and the source, very, very low, that the value of the resistance can be controlled with the gate to source voltage. You put the highest possible gate to source voltage just before transistor breaks down, you get lowest possible RDS. Shortest distance, shortest resistance between the drain and the source, and that can be really short, like few tens of milliohm. Then the saturation region. So once we pass to that side, ideally, if we assume the channel does not retreat, doesn't shorten because of the drain to source voltage, and the lines are constant, independent of the VDS, then this equation would be adequate without that to calculate VGS against the ID, which is nothing but the transconductance curve. But if they depend on it and you know the lambda, by simply taking one of those curves, 2 points on it, extend it, cut it, flip the value of the voltage you see there, that's the value of the lambda. And this equation is going to be mathematically more accurate function. However, in most calculation, they discard lambda, they assume it is 0, and you end up here, parabola. And in this parabola, ID will be 0 whenever VGS is less than or equal to VT. Here, 0. When VGS is greater or equal to VT, the parabola will pick up. If you are operating at a gate to source voltage drain current, in other words, you're operating at a point here, you have ID, you have VGS value, a small change in the gate to source voltage, inducing the small change in the drain current can be related with a coefficient called GM, just like transistor. Small collector current is GM times base emitter voltage, small change in base emitter voltage. Here, the IC over VT is gone, is this one. This is like similar to IC over VT. It depends on drain current. There, it would depend on collector current. And Kn is the conductivity constant, which depends on the geometry, area, mobility in the semiconductor. This will be given to you. Kns will be given to you. And in case if there is a lambda that you know, then it can be incorporated in this equation, knowing the D point, the Q point, knowing its ID, knowing its VDS. You cast it into this formula here, VDS and ID, knowing lambda. You can get an idea about the drain to source dynamic resistance, which should be included here in the small signal model. But we scarcely get to that point. So this will complete both AC and the DC analysis of all MOSFET circuits to come. Okay? So let's see how much time is left if I can solve the problem. If not, we will come back on Wednesday and we will start problem solving. So let me see.
You have about 8 minutes.
8, no, that's too short. 8 minutes is too short. So you know what, I will give you the problem with work, try to solve it. When you go home, you have something to think of. Okay, so let me just, I can put that, I can do that. So if you want to take a picture, just a good reminder, take a picture of this all the way on both sides. So you will have for your reference, and it will remind you, when you look at it and you go through, it will remind you how it is going to be used. Okay.
Can you tell me the name of what Kn stands for?
Kn is called the conductance coefficient, Kn. Conductance coefficient. It has a formula that calculates. I didn't go into that here. Kns are known as conductance coefficient. Unit is ampere per volt squared, or more commonly milliamp per volt squared. So if it is given to you as milliamp, let me tell you something you won't confuse. If Kn is given to you as a milliamp per volt squared, stick it here. Don't change it to ampere. Just place it here. ID will be automatically in milliamp. V will be in volts. Resistors will be kilo ohm. Continue with the calculation. So that's what it is, conductance coefficient. Conductance coefficient Kn is equal to K dash N, I'll tell you what that is, multiplied by W over L. L is the length, W is the width of that plate, this plate at the top. And K dash N will be equal to mu N, mobility in the N-type material, multiplied by C2 dash OX. This C2 dash OX is is epsilon OX divided by T OX. T OX is gate separation epsilon OX is insulation dielectric, and mu N is mobility. N-type mobility. Kn can be easily controlled, that's the great thing about the MOSFETs, with the W over N ratio. So you want to make different gains, just spread, make it wider, make it deeper. It will increase it. You can keep all of them with the same length, and some places you need more gain, extend that on a masking operation. It's very, very compatible. I think this is a transistor that will stay forever. Okay, so let me just give you that problem. Let me see if we can draw it or not. No, 3 minutes is left, no. We will come Wednesday, okay? I'll put the problem on the board so you won't panic, when you're retrying. We'll do a tutorial in the class.
Are we expecting this on the midterm next week?
Yes, this can show up in the midterm. It's BJTs, MOSFETs, circuits, but it is so close to the all of that we have done that I won't spend that much time on that one. Maybe 1 lecture, 2 lectures, just enough, more than enough. It's the same model, same everything. Same method of analysis. Okay, so let me erase this.